Well, this is question from May June 21, 9709, variant 32. Question number 4. This is question on integration by parts. Using integration by parts, find the exact value of, so you're given a definite integral tan inverse of half x limits from 0 to 2. For integration by parts, as we know that we need two functions, but here just one function is there, and there is no direct formula for the integration of tan inverse of half x. So, so in MF19, so you don't have any formula. You can't find any formula for the integration of tan inverse of a function, tan inverse of half x. So, as hint is there, integration by parts. So let us write this thing as tan inverse of half x. The other function you can take as 1. So into 1 and then dx. So what we do for integration by parts, first of all, we write the formula from the formula sheet. The right hand side of the formula of this integration by parts. This is integration by parts in MF19. So the right hand side is uv minus integration sign v du by dx. So without wasting time, write the right hand side of the formula, and then what to do next, I'll explain. So write the right hand side uv minus integration sign v du by dx, and so after writing the right hand side of the formula, we decide u and dv by dx. So uh, in this case, so there are two functions. Let let u is equal to tan inverse half x and dv by dx. So as I said earlier, one is u, the other is dv by dx. So dv by dx is obviously 1. You can't change the order because the function which I've taken as dv by dx, we integrate. So when you integrate, integration of 1 is x, and the integration of dv by dx is just v. So we integrate and we differentiate the other. We differentiate, yes, you can differentiate. You can find du by dx. We can find du by dx. So from the formula sheet, let us check what is the formula for the differentiation of tan inverse of x. The differentiation of tan inverse of x. The differentiation of tan inverse of x is here. These are the formulas for the differentiation in your formula sheet. So the differentiation of tan inverse of x is 1 over 1 plus x here. So what is the problem here? You can't apply this formula because it's not just x in the, it is not just x here. It's not just x, it is half x. We have different function here, not just x. So what you can do, I can give you the improved form of this formula. So the top one in blue box is the formula which is there in MF19, tan inverse of x. So if it is not x but fx, any other function here after tan inverse, so this, for this case, you can change the formula as follow the same order 1 over 1 plus 1 over 1 plus, and then fx whole square into the derivative of this fx, which is f dash of x. This is the formula. You must keep in mind this formula. So what is the reason for writing this form? What is the logic behind this? So the proof is very, very simple. You can apply the chain rule for this proof. So here we have y equals to tan inverse of fx, and we want to find dy by dx for this tan inverse of function. So you don't need to show this working directly. You can write this formula. Uh, let let u is equals to fx. Then obviously if u is equals to fx, then y would be tan inverse of u. Then after writing u equal as fx as u, you can differentiate both. Du by dx is f dash of x, we know, and yes, tan inverse of u. The differentiation of tan inverse of u with respect to u is 1 over 1 plus u square. So du by dx is there, dy by du is there. I'm looking for dy by du. You can apply the chain rule, and here is the chain rule. Dy by du multiplied by du by dx is dy by dx. So dy by dx is here, which is 1 over 1 plus u square. Du by dx is here, which is f dash of x. So finally, writing u as u as fx, you can write this form of the formula. So 1 over 1 plus fx, if it is not x in the tan inverse, if it is not just tan inverse of x, if it is tan inverse of half x or any other function. So this formula is applicable for all such cases. So 1 over 1 plus fx whole square into f dash of x into f dash of x. This is how. So keep in mind this formula which is in red box. So if it is not just x, so if it is just x, we just wind up the situation here, 1 over 1 plus x square. But here we have a different function. As the case is here, we have 1 over 2x, we have half x here. So 1 over 1 plus 1 over 2x whole square into the derivative of 1 over 2x, we know is 1 over 2. You can always simplify 1 over 1 plus x square over 4 into half. This is, I'm simplifying du by dx expression. You can take LCM 1 over 4 plus x square over 4. You can do it directly. 1 over 2, and this 4 can be shifted in the numerator. 4 over 4 plus x square into 1 over 2, and so we have 2 over 4 plus x square. When you simplify, this is du by dx. This is du by dx, and yes, we need du by dx for this right hand side. So after letting u as tan inverse of half x and the other dv by dx, one as dv by dx, so you integrate that dv by dx, we have v. So after collecting all these things, let us use here in this formula. So you have you had du by dx. So I'm just highlighting this thing. I'm highlighting. This working is very, very important. So using all these things here in one. So put in one. Left hand side is tan inverse of half x multiplied by 1. You don't need right here. Equals to u into v. U is here and v is here. Multiply them. So tan inverse of half x multiplied by x. Tan inverse of half x, tan inverse of half x multiplied by x uv minus, there is integration sign, minus integration sign, then it is v, v is x, v is x, and du by dx is 2 over 4 plus x squared. So I just replaced. So u is multiplied by v minus integration sign v is x, and then 2 over 4 plus x square, which is du by dx. So after writing these things here is equal to, you can simplify x tan inverse of half x minus integration sign and then 2x over 4 plus x squared dx. Still we have this integration sign there. Still we have that integration sign there. So how to integrate this part? How to integrate this part? 2x over 4 plus x squared. Now, for this case, you can recall the formula. You can recall the formula which you can find here in your formula sheet, the integration, yes, this formula. F dash of x over fx. You can keep in mind derivative. This is basically the derivative in the numerator over function. If it is derivative over function, write natural log of function, natural log of function, natural log of the denominator. So in this case, fx is the denominator. Fx is the denominator. So here, what I can do, I can let this denominator. This is derivative function. There is no other option. So let us write the working here. This is the working for the second part. If you take fx is 4 plus x square. What is f dash of x? It is 2x. So it means that, uh, or you can write for your understanding this as we have x tan inverse of half x, the first term. You can do it directly, or you can write this is now using this working f dash over f dx. Next is x tan inverse of half x minus natural log of f, which is x tan inverse of half x minus natural log of 4 plus x square. You can write this directly from here. So as this was question for a definite integral, the limits are from 0 to 2. So in the end, after completing this whole working, what you can do, you can write the limits tan inverse of half x. This is the answer. But if there are limits, yes, you can always use the limits, upper limit minus lower limit. So upper limit is 2 tan inverse of 2 over 2, which is 1, minus natural log of 4 plus upper limit, 4 plus 4, 8. This is how you can apply the limits. Upper limit minus the lower limit. This would be 0 because 0 tan inverse of 0 is 0, minus natural log of 4 plus 0 is 4. Tan inverse of 1 is pi by 4. Using the radian mode of the calculator, you can get this answer. Minus natural log of 8 plus natural log of 4. Simplifying, you can write equals to pi over 2 minus, you can take negative common, natural log of 8 minus natural log of 4. Next, you can apply the properties of the log, equals to pi over 2 minus natural log of 8 upon 4. And finally, we have the answer in the simplified form, in the exact form, pi over 2 minus natural log of 2. This is the answer to this question. The answer of this definite integral, pi over 2 minus natural log of